Okay, so welcome to our September 11th meeting of the RASC Ottawa Centre. My name is Dave Chisholm. I'm the meeting chair for this meeting. And a special welcome to those who are here from other RASC centres. And we also have a special guest this evening, Dr. Christian Sasse, who's going to be talking to us about the iTelescope project. So we move on to the next screen, please. Couple of security things around Zoom. I repeat this every month. It's important for us to be aware. We do have a chat box, but I will not be monitoring the chat box during the meeting. If you have questions, please use the Q&A box. Do not raise your hand. I think we have that disabled. But if you do raise your hand, I'm going to ignore you. Please use the Q&A box. For your security, do not click on any web links that might appear in the chat or the Q&A windows. This is sometimes hackers will get in and try to direct you to bad websites. Okay, that's it for security. Next slide. Okay, so here's the program for tonight. We're almost through the introduction. I've got a 10-minute astronomy news segment, Ottawa skies for September. We have Dr. Christian Sasse, who will be doing the iTelescope. We'll take a 5-minute break. And we have a ton of observations this evening, and some of them will look really awesome. So I'm looking forward to that. And then we'll finish up the meeting with announcements. Given the number of observations, get yourself an extra coffee. We may be here till 10 o'clock. I try to finish by 9:30, but given the number of observations we have in, it may stretch a little bit. Okay, next slide, please. So we have a bunch of new members, so welcome to the RASC Ottawa Centre, and 54 new members in 2020. That's not too bad given the current pandemic situation, so welcome everybody. Okay, so let's move into the 10-minute astronomy news. Next slide, please. Okay, so this is basically a report written by Nicole Mortellero of the CBC. I thought it was a very well-written report, and so I'm going to read it to you along with the graphics, and it's quite an interesting phenomenon that they've discovered. So a team of international astronomers has caught the merger of two black holes of unprecedented masses, creating yet another massive black hole, one that the astronomers believe existed in theory, but had never been detected. The two caught in the act were roughly 85 times and 66 times the mass of the Sun. After the pair merged, producing a gravitational wave picked up by detectors, it created a black hole of 142 times the mass of the Sun. We've never seen anything like this before, said Evan Goetz, a research associate with the University of British Columbia's Physics and Astronomy Department, and co-author of a paper published on Wednesday, September 2nd in the Astrophysical Journal Letters. This is the first time any type of gravitational signal like this has been measured. The discovery, called GW190521, was picked up using Laser Interferometer Gravitational Wave Observatory, or LIGO, detectors in the United States and the Virgo interferometer in Italy on May 21st, 2019. Next slide, please. So far, gravitational waves, ripples in space-time caused by highly energetic processes in space, such as the merging of pairs of black holes or neutron stars, or a black hole in a neutron star, typically create a sort of chirp noise on the detectors. But this one, the researchers say, created more of a short-lived bang, producing only about 5 or 6 waveforms, which can be thought of as actual waves that oscillate. Comparatively, other gravitational wave detections have produced hundreds of waveforms. Due in part to its brief signal, astronomers had to ensure it wasn't noise that was causing the suspected detection. Now that it has been confirmed, it is the first of its kind and is shedding a light on the elusive member of the black hole family, intermediate mass black holes. There are 2 special parts to the findings. One, the sizes of the pair of the black holes, particularly one that is 85 solar masses, and 2, the final black hole itself. Black holes are regions in space where gravity is so strong that nothing can escape them, but they're not all created equal. According to theory, stars that are roughly 10 times the mass of the Sun can die in a massive explosion, a supernova, that can produce a black hole Stars that are roughly 65 times more massive are believed to destroy themselves, but stars that are more than 120 solar masses are believed to collapse directly into a black hole at the end of their lives. So that means black holes between 65 and 120 solar masses shouldn't even exist. Yet this new discovery contains two that fall within that range. The one that is 85 solar masses is particularly intriguing because it falls right in the middle of those sizes. So we're just going to watch a short video, which is a simulation of the merger of the two black holes.
In May 2019, LIGO discovered the most massive black hole merger ever observed. Two monster black holes collided to form an even more massive object, about 150 times as heavy as the Sun. Not only was this the first time an intermediate mass black hole had ever been directly observed, but one of the monster black holes that created it shouldn't even exist, according to standard theories of how stars die. At the end of their lives, stars of the mass over 10 times larger than our Sun explode in a supernova and leave behind a black hole. But stars with a core mass over 65 times the Sun destroy themselves completely, leaving nothing behind. However, stars with a core mass over 135 solar masses avoid this total destruction, collapsing directly into a black hole. So black holes between 65 and 135 solar masses should not exist. There are two leading ideas how it formed. Maybe it was made of smaller black holes which merged together, building up progressively larger black holes. This could happen in a dense environment like the center of a galaxy or a globular cluster. Or perhaps a star late in its life collided and merged with another star, making it big enough to form a massive black hole whilst avoiding total destruction. The resulting intermediate mass black hole is the missing link between the two known populations of black holes: stellar mass black holes with masses up to about 60 solar masses, and the supermassive black holes that exist in the centers of all galaxies.
Okay, next slide, please. So this chart compares the GW190521 merger event to others witnessed by LIGO and Virgo. The black holes created by the merger falls into a category known as an intermediate mass black hole. And this is the first clear detection of a black hole of this type. There are stellar mass black holes, which astronomers believe can go up to 10 to 100 times the mass of the Sun. Then there are supermassive black holes, which can be found at the center of most galaxies. These monsters can come in at millions or even billions of times the mass of our Sun. While there have been theories about those black holes that are 100 solar masses or higher, called intermediate mass black holes, none have been directly observed until now. There's been no observational evidence prior to this discovery, Goetz said. This is the first conclusive evidence for an intermediate mass black hole. There are two leading theories as to how these seemingly impossible things have come to be. One is that two stars could have merged to produce a black hole within the 65 to 85 range. The second is that multiple black holes could have merged within a dense star cluster, creating larger black holes of differing masses. This is kind of exciting, said Priya Natarajan, a theoretical astrophysicist and a professor of astronomy and physics at Yale University in New Haven, Connecticut, whose main area of study is black holes. She was not involved in this particular piece of research, but in a paper published in 2014, she and her colleagues proposed that the creation of black holes, similar to the 142 solar mass one discovered last year, could have come within a dense cluster of stars, much in the way the new discovery has been observed. The idea is one of the stars becomes a little black hole and starts wandering around, and it's kind of fed by the fire hose of gas that grows very fast. Then it becomes massive and it grows to about 50 times, and then it sinks to the center. The second guy would roll around, but it wouldn't grow as fast because there wouldn't be as much gas left over. And so we predict that if you make two in that way, they cannot be the same mass, they will be different. And that's what is seen now. So that is kind of exciting. While the discovery is a first, the astronomers know that they need to increase their sample size to adequately explain the existence of intermediate black holes. We need more observations of this type of signal, so more mergers that yield intermediate mass black holes will help us to understand how they're formed, Goetz said. Black holes play a key role in so many aspects of astrophysics that we're only now just beginning to understand much more deeply with these observations. And more importantly, they will help us understand how we got here, as black holes are key to the creating of much of what exists. It's part of the origin story of our universe, Hadarajjan said. We may not have been here if our Milky Way did not have black holes. Okay, next slide, please. So we're going to take a look at the Ottawa skies for September. So next slide, please. Haha, you missed it. The full moon was on September 1st. September 2nd. And this full moon was known by the early Native American tribes as the corn moon, because the corn is harvested around this time of the year. Next one. So as you can see, our days are obviously getting longer by the sunrise and sunset times through the month. I certainly noticed it in the evening. It gets dark quite quickly. Next one. So Mercury is not really visible this month, but October 1st, which is before our next meeting, it's going to be at the greatest eastern elongation on October the 1st. You look for the planet low in the western sky just after sunset. Venus is visible before sunrise. Mars is visible in the evening and through the night. Jupiter is visible in the evening through the night. Saturn also is visible in the evening through the night. So this is great. We've got 3 planets that are quite easy to see in the evening skies right now. Uranus is visible all night, and Neptune is visible all night, and it's at opposition, which is closest to Earth, on September the 11th, tonight. Okay. And here is our cartoon of the month. This never happens, does it? Okay, we'll move on. So I'm very pleased to have Dr. Christian Sasse, who's going to talk to us about the iTelescope project. And I have been accumulating my points to capture some images, but still haven't quite done it yet. So I'm fairly new to iTelescope, and he's going to explain how the whole process works. Dr. Sasse. And he needs to share his screen here. So let's give us a second.
Okay, I hope you can hear me.
Yeah.
Okay, very good. Well, first of all, thank you very much for giving me the opportunity. So I am your counterpart on the West Coast. I'm based out of Vancouver, and my name is Christian Sasse. I actually immigrated to Canada in 2007. I was an electrical engineer before, and I joined iTelescope 2 years ago because I wanted to do something very different. And then I got spent a lot of time in Australia, absolutely wonderful. For those of you, I've seen it, I've seen Chris's recent presentation on Namibia. If you've been to Namibia, if you've been to Chile, Australia, or any of these beautiful southern skies, you'll know that the southern sky is a lot more beautiful, at least to the visible eye, than the northern hemisphere where we are, right? It's quite remarkable. So anyway, the advantage of that brought me, my love to Australia. I got to know iTelescope much more, and eventually got employed there. And that's probably the most exciting job you can imagine, because I get to deal with very nice people, contrary to the electrical engineering industry where I was before. It's actually very pleasant. The technology is very complicated. You can imagine that those of you who are technical geeks, what's going on behind the scene to run telescopes is very different to what you have in your backyards. I have my backyard telescope. I'm sure many of you have that too. And it's surely quite exciting to have that, but to run it remotely is another story. So I'll give you an introduction to iTelescope, and thank you for giving me the opportunity. And do feel free to ask questions. So I'm going to share my screen now. Let's see, here we go. Okay, I hope you can see this. So that is the welcome page of iTelescope. We are, by the way, completely revising our website now. Technology is changing at such a fast rate, and we need to catch up too. A lot of the astronomy software, as you know, originates from the 90s and 2000s, and the old Fortran codes that we know originate much earlier, of course. At the same time, you get these beautiful apps on your iPhones. We've seen it with Comet Neowise, which you see behind me, that was taken at Lake Harrison in beautiful British Columbia. And it just gives, it's amazing how these apps are developing, and we need to catch up too. The whole way astronomy is presented to the world is rapidly changing, because it used to be that the astronomers or anybody who has to join has to be very knowledgeable. We're trying to take that away, similar to what the apps are doing. Many of those which you know on your smartphones, we're trying to take a similar approach. So that's the main page of iTelescope. Once you subscribe, you come to what we call the launch pad. That's still a little bit of an archaic view, honestly, and we are revising this in the next 2 years. So the way it is, so you see a map of the world here on the left. I'll explain that to you in a moment. And by default, we have several observatories. It's supposed to be dark somewhere around the world at any time, you know, during the day. That's the idea. We're actually getting a lot more observatories to coming online. COVID has shown a rapid explosion. Davis just mentioned that. You know, we've seen the same, one of these incredible niche areas where we got a surprise increase of membership and interest, which has given us the funds to expand further observatories, especially in the Southern Hemisphere. So let me just explain this quickly. I'm just going to expand the window. Now, this is not correct. You know, I just noticed it. We have a server error here. That's the map of the world, but we're supposed to be here in light. We're in darkness. So the day and night time, we have to reset the server, is not correct at the moment. But you can see the current position of the moon, the sun. That has shifted a bit because the moon is much lower at the moment. But anyway, what it tells you, if it is correct, we have to reset this, is whatever is in darkness, the red dots is where our observatories are. So that's Australia. Then we have Spain in Europe, and then we have New Mexico skies, and also one in California, and we're adding another one in Chile and so on. So a lot more coming up now, which is very exciting from the astronomy world. So the question always for the newcomer is, what on earth do I do with all your telescopes? And that's a very relevant question. It's something we're trying to address to make things much more user-friendly, right? You have all this. So by default, anyway, the window's open where it is nighttime. You can see Astrocamp, that is at the moment in Spain. They've got 2 systems offline at the moment, which are being maintained. That happens quite a lot because of the frequent use, of course, that we have. But let me just expand this window so you can see it. So you can see you've got a very clear sky there. On the top row, those are the astronomical sunset and the astronomical sunrise. So they have not really something to do with our sunrise and sunset. It's when it gets exciting for astronomy. On the next row is the current position of the moon. So you can see there's an arrow pointing upwards. If you look carefully, it's at -2 degrees. So it's just coming up, above the horizon. That's of course very, very important. That's 34%, which is very good for observations at the moment. And below that, you can see the current position of the sun. There's a downward arrow, so it's -47, so 15 degrees per hour. You may know this approximately. So it's about 3 hours after sunset there. Then there's a link here to the weather, and that's really important for remote telescopes. You'll appreciate that when you do things remotely, you have to completely think differently, right? It's something doing in your backyard. When something goes wrong, you can just jump out and you have a look at the weather. You immediately understand intuitively why things don't work out. In remote telescopes, in remote astronomy, it's very different. So let me just click here on sighting spring. You can see it's daytime there, of course. Sun is out now. And if you click on the weather, that's the most important link, right? You can see that's our biggest observatory. We have the biggest roll-off observatory there in the world. It's half of it is actually hosted, and the other half is for everyday use. And you can see here's a map of the area there. You can see it looks very clear. Coonabarabran, for those of you who've been in Australia before, will know that's in New South Wales. It's of course in a very dark area. It's where the main astronomy in Australia is taking place, near Coonabarabran. It's quite a famous place. Let me just close this again and get back to the weather here. So Yeah, what is missing here, I can see unfortunately, our weather, our roof status has just broken down. So we need to get it back online. But usually what you see here is the roof status. If everything is green there, I'm sorry, I'm talking here and something that you cannot see, but usually the interface here, it's coming back up, is it? Yeah, here it is. Here it's coming back up. It's back online. Yeah. So that's what I wanted to show you. So this is quite complex, right? If you run your own observatory, it's fairly easy to open and close. But because of the assets we have there, you can see we're using two different weather stations. One's Boltwood. You may know the name, of course. That's a Canadian, by the way, Boltwood. And the other one, Davis. And this was designed, and we have two different weather stations that have to run independently, and they all have to show green lights in order for the roof to open. So of course, at the moment, the roof is closed because, well, it's very light. That's the main reason. But well, usually we have quite good conditions in Australia. The site there is on an old supervolcano. It's relatively high, and the conditions are usually very good. Not as good as in Chile. Chile has the best skies in the world, much better even than Namibia and so on. Chile, Chile ranks #1, and that's also why most of the southern observatories are actually in Chile. But we're not bad. We're not bad either in Australia. It's definitely like Namibia and so on. Similar skies that we have there. What's interesting, maybe for those of you who are tech geeks, about the roof, so I'm deviating a bit and telling you some interesting stories here, is the roof doesn't really depend only on the weather. If we lose connection for any reason whatsoever, the roof will always close automatically. So it's very important that when you have a roof design, it runs independently of your astronomy software. You can imagine how these things go wrong, and they do go wrong. Any astronomy software will crash sooner or later, and this will always close no matter what. So it's like a heartbeat, and if the heartbeat stops, the roof closes, and that's it. So it's important to always have a look at the weather. Yeah, let's come back now. So this is an overview of all the telescopes, and I'm sure you will not know what they all mean, and I don't blame you for that. So how do we then get a newcomer going? The window, what we've recently added is an icon called Start Planning Here, and that works together with a beautiful website. It's called Telescopius, right? It's an Argentinian software developer whom we know very well, and he's created a site that's quite visual and makes it a lot easier. So we have these different observatories: New Mexico skies, Northern Hemisphere Sierra, Northern Hemisphere and Astrocamp, and we have Siding Spring at the moment in the Southern Hemisphere. So you can first choose your observatory. Well, we're getting nighttime, so let's have a look at New Mexico skies. You can see there's a field here for the dates. If you leave it blank, it will default to the next opportunity, which is tonight. And then you can choose different objects as you wish. You just press search, and it will show by local time. So this is all the local time in New Mexico skies. It'll show you the visibility, the rise time of the object. I'll explain that in a moment. The transit time, that's the highest time, and then the set time. And it's usually done for those objects that are brightest, or the targets that are brightest, and downward. So you can easily select something. We've made it easy that you do not need to understand the astronomy. You don't have to understand anything about right ascension and declination, but those of you who like that, they can copy and paste it into the into the menu that I'll be showing you later. So all you really have to remember, if you don't know what's going on, well, let's take Andromeda for a moment. I'm just going to copy the name like this. 1 second. Control copy. That's for later. And let's say we know nothing about this object. Well, since we're talking to Astronomy Club, I can tell you the magnitude of 3.4 will tell you, of course, that that's a very bright object here. The size is quite bright, quite large. Of course, the moon diameter is 0.5 degrees. So we're talking at least 6 moon diameters, which is large. What is very important is the angle to the moon. We've included that. So 77 degrees away from the moon at the moment is absolutely no problem. The moon is low anyway. It's not going to disturb us. But when the moon gets quite high, you have to pay attention. And when the moon is full, the angle between the moon and the telescope, and I'm quite sure you know that from the backyard, should be somewhere around 120 degrees in order to get anything decent. The moon gets really a big nuisance then. So that is the rise time above the 30 degrees horizon. We define it by 30 degrees and not by the horizon because most observatories start seeing things properly at the 30 degrees horizon, and the same is for the set time. Let's jump in, and this links us to Telescopius. Some of you may know this. It's a beautiful website. It's completely free, and I encourage you to sign up with that. It will automatically bring you to the target that we're looking at. It'll automatically select the correct observatory. As you can see here, it's New Mexico skies. And what I really like here is it's very visual. I'm a very visual person. I like to see things, you know, not so much in numbers, but they're getting very good at this. You can see that is the green line. That is the horizon line. There is the daytime, the black is the nighttime. So you can see it gets visible around somewhere around just 9:11 p.m. That's the highest point in the sky. And then in the west, we have to stop observing. Well, actually, when twilight comes in the morning around 6, just before 6 a.m. And then it goes below the 30 degrees horizon during the day. So that's great. So what telescope do we know? We know what object to take, but how do we know what telescope to take? And this is where we have worked together here with the developer. You can see here it's already marked on iTelescope. If you click on the top window here, you'll see we have a selection of different telescopes. Now, the program is not intelligent enough that it'll know the difference between Australian and US telescopes in this case, but we do know that New Mexico skies is in the US, so we can choose any of these. I'm just going to click on one of them for fun. And just let me get this. And you can see Andromeda, of course, that's why I chose it, is a huge object and definitely not for this type of telescope. So T24, you can see is a 24-inch. It's a huge telescope, right? And you can see the field of view is half a degree. Well, that's definitely not sufficient. So in order to take Andromeda, we definitely have to choose another telescope. So I'm just going to scroll down. Let's try this one. That's a refractor. I'm just going to click on it again. And that actually fits in very beautifully. So you can see T14 or T20 would give a very nice frame. Now we cannot move the frame. That's what you can do in your backyard. You can turn the camera around, or some of you may even have a field rotator. We don't use field rotators because it's all about reliability. Reliability is the key thing for users. And a lot of these innovations that are there, such as field rotators or Alt-Az, to do the correction instead of doing an equatorial or German equatorial mount, which we typically use, we try and keep things very reliable. So that's why the field of view that you see there is very fixed. North is up, and you can see most of them are almost either north-south facing or east-west facing. You can also later, by the way, if you I'm just mentioning that here, if you like to move the window around, you can move the background and you can frame your own picture, and you can then copy the coordinates of that around to frame it exactly. You can also do mosaics and so on and so on. A lot of possibilities. You can do comets now. After NeoWise, there was an incredible interest in doing comets better. So they've improved the website because comets for a lot of people is quite complex because of the unknown position, many of the tail and the orientation, of course, of the comet and so on, and it's moving. It gets quite complicated, but that is becoming a lot easier now, as things develop. Okay, so we know the object name now, and we know the telescope. So I just said T14. What we just saw that it's nearly visible the whole night, so we don't have to worry about it. So what do we do with it? Well, with telescopes nowadays, you do only reservations. We don't allow really online viewing anymore as we did before, where you just reserve a spot, simply because a lot of these people didn't turn up. Well, I don't blame them, it's nighttime or whatever. So you always have to have a reservation. Well, the telescope is quite dumb as such, it doesn't know what to do. So we have to explain to it what it's going to do. So let's do that now. Let's jump into T14. So that's New Mexico skies. You can see it's still daytime. I can click on it, and then every telescope has its own IP address, right? So this has got its own IP address. I jump in, that's a picture there. It's a beautiful refractor, as you can see. And now we want to tell the telescope exactly to take Andromeda. That's what we're going to do. There's a menu here on the left-hand side, and it's the same menu, just like you drive a car. The technology is very much the same from car to car. It doesn't matter what type of car you do. So the menu is the same for us. You have a menu called one-click images, but that is really not advisable to do, because when you click on it, it's really a black and white image. It looks a little bit deceptive, I know. We do have some color images, so color cameras too, but we didn't change the menu to reflect the black and white. And also you will not get the beautiful resolution of just a single 5-minute image. But if you don't know what to do, you would just submit there. But careful, at the moment, of course, the observatory roof is closed. So this wouldn't be very advisable. The most important menu is what we call the deep sky menu. So I'm going to give it a file name. I'm just going to call it test at the moment, because you can give the plan any name you wish. Or the target, let's see if it remembered. No, it didn't. I'm just calling it M31 in this case. It should find it because it's a very common object. And here you can see it says the target is found. Automatically, the right ascension declination is put in. You don't have to worry about it. Now, the important thing is when you start image, there you go. That's what we just looked up, the transit time and the imaging time. So it's a perfect time, of course, for an object like that. Gives us a lot of opportunities, right? So the next thing we have to do is choose the filters. Now, many of you will know about astronomical filters. It's very different to your DSLR, right? So this is definitely a camera. This is definitely a telescope that is working with a CCD camera. It's not the new CMOS technology that we are seeing an increase in rise. The CCD cameras still have a big edge on the CMOS cameras in many ways because of the sensitivity they have, but that's going to change very soon. Many CMOS cameras are getting to the 16-bit range, and they are slowly replacing the CCD cameras. But anyway, we have the CCD cameras. They work very well. So how would we do an object like that? Well, typically you mix the colors. The luminance is the black and white, really. It's the old-fashioned black and white. It takes the whole spectrum of the of the camera into account. Typically, you would take 3 of that for an object like that. And very typically, you take 300 seconds. That's the exposure. So we do a 5-minute exposure for luminance. And then we need the colors too. Well, the most efficient way of doing that is now we need red, green, and blue. So I'm just going to put that in. Red, green, and blue, 300 seconds. But I'm going to do this on bin 2. For those of you who don't know what binning is, it's not something we have in the DSLR camera. It's the assembly of putting pixels together in a superpixel to make it more sensitive at the cost of resolution. We lose resolution, but we get the color, the resolution we're getting through the luminance, right? So it just gives us more, how should I say, more signal in a shorter time. That's what we're looking for, because time's also money after all, right? So red, green, it'll be the same thing here. And also put it on binning 2. You have to be careful that you have the same binning there. And the same goes then for blue. And that would basically do it. That would be, you can see the maximum exposure is 1800 seconds. It's half an hour. That's very good. I would not recommend doing that because in general, Andromeda is a very bright object. Within 5 minutes, you will reach saturation very soon. So 5 minutes is usually a good thing. 1800 seconds is for narrowband. That's really, if you narrowband, you need a good signal to noise ratio. You need to integrate time-wise as much as possible. So for narrowband, you would use 1800 seconds. There you can see the minimum, the the target that's allowed is 25 degrees. So anything above 25 degrees in this observatory for this particular telescope is okay. You can dither. For those of you who know what dithering is, it's taking account or trying to compensate for any problems that we have on the CCDs. In CMOS, you won't need that so much anymore, but CCDs sometimes have bad columns, and you can compensate by that by just moving the telescope a little bit up, down, and sideways. So you usually dither, and then all you do is click Create a Plan for later. And if that plan looks fine, I haven't forgotten anything, it'll say, I've saved that plan, thank you very much. So now you have the plan, and now we need to somehow relate that to the telescope. And that's fairly easy. So what we do now is you go to make a reservation, right? So let's see if we find a gap here. Well, you can see at the moment, of course, this is a very popular telescope. So at the moment, this is quite full. So that is not a surprise because the moon is low and so on. So it's unlikely we find something at the moment with T14 at this time. However, there's someone doing here you can see someone is doing M31 right there. So we probably could find a gap here just, as the full darkness has ended. So that would go for, I think, tomorrow already, or Sunday. Yes, for Sunday it would be fine. So the question is, how much time do we need? The total image time was, per filter, we had 5 minutes times 3 is 15 minutes. We had 4 filters, it was 60 minutes in total. But as you know, telescopes slew and take time to move. So the recommendation in general is to reserve for 90 minutes. Now the cost is only per image, has nothing to do with the reservation time. So if we start imaging at 4:30, I think that was the gap, we would have to go at least to 6 o'clock. I don't know if that's possible. Yes, it is. And we would then attach our plan, and that's all you need to do, and you're finished with confirm reservation. You can reschedule automatically. So if the weather's bad, it'll try and find a new slot for you wherever one is free at the same time. And that's it. It's really simple. Now you can move this around too if you want to. I could try and move it. I can't move it here because the roof is already closed, but you can move this by hand by just dragging it to other days too if you wish to move it around. And that's it. It would run by itself. You'll get a log file finally. I'm just going to show you what the log file looks like. So you can, by the way, also see the system status here. That's the observe. Now this looks very much like hieroglyphics, but it's not. It's just the. This is just the telescope running at the moment. You can see the telescope is stopped. There's nothing going on. You can see filters and all kinds of other things here. And when it runs, you can even preview the last image if there is one. Sometimes there's not. Let's see. Well, that was probably a calibration image, but there's nothing here at the moment. And then finally, what's very interesting is also for you to know, you have your observing plans here. I'm not going to go into that. You can click on them and you'll find what you've done there in script file. And also what is interesting is your run log. So once you've run your, once it's run, sometimes things go wrong, right? I mean, that you know how astronomy worked. You saw the picture before, clouds come in and so on, or the roof closes, or maybe the focuser didn't work and so on. So it's important sometimes to see what your run looks like. So I would go into the folder. I'll just go into an old folder here and click on view. Okay, that wasn't, maybe it's deleted already. 1 second, this was an old one. Let me try here. Oh, there it is. Okay, so that is the plan that ran. Okay, so it shows you everything, right? It shows you the plan was okay. It's been running and so on and so on. And you can see here something happened. There was an error in the software, which happens rarely, but it does happen. But it's a good example because the system crashed here. And it stopped. So in this case, it started focusing, the plan started running, and there was something wrong with the telescope. So it'll give you that message. But in most cases, that fortunately doesn't happen. In most cases, you'll see that the run has been completed correctly and the image has been taken. But it's important to have a look if things do go wrong, which happens, right? Yeah, what else is important there? You can have a quick look here at the observatory if you want to see what's going on behind the scenes. I mean, for those of you who do backyard astronomy will recognize what's going on. Maxim, of course, actually developed also by Canadians, is a very, is very well known, of course, from the software. As for the camera control software, there are very different softwares now. We have the observatory software that we're running here, but we run a very modified one called ACP, and that's the sky and so on. And then we have a focuser and all the other things. There are lots of things going on in the background, and that's why things can go wrong. Okay, then finally, what you would need to know, of course, is where are my images, right? So you just click on my image files, and that brings you onto a data server, as you can see here. So I can log in here into the data server, and let's just take a bit of time. Okay, wait a second. Not sure. At the moment I'm logging in as an admin. Maybe that's a bit difficult at the moment. Let me just see. Let's see if I can find my other name. 1 second. Let me try with my own name. Oh, there we are. It's going in now. Okay, that's fine. That's fine. Okay, that's all good. Seems to be connection is a bit slow. But what you find here is you'll find all your images. I'm just going to jump into an image file here just to show you what it looks like. So here you can see that's a telescope name, that's the object name, then comes the date, and there so we pre-calibrate things because calibration is really a pain. So all the calibration, that means taking the flats, the darks, and the bias frames are automatically corrected. So that's why it says here calibrated, which makes it very easy for image processing. You could go into softwares like AstroPixel Processor, PixInsight, or whatever you have, and you go on from there. So it's calibrated. That's the name of the telescope. That is the wait a minute. That is the date and the time. That's the object name, and so on. You can see this was taken with a luminance bin 1, east side 300 seconds, and so on. So all the information is there. It's a FITS file because that's the astronomical norm that is used there, where all the information of the observatory and user and so on is stored, which is very important for image stacking, which is done later. So you can download these then, and usually within a few minutes after you've taken the target, you will have your images there, because we're using very fast servers. And I think that's really it in a nutshell, because you may have questions, so I'd rather jump back to the main page and thanks for the time, and just give you some opportunities for questions.
Okay, so if you have a question, folks, please type it into the Q&A box. Maybe, Christian, if you can explain how your point system works in terms of getting access to the telescopes. It's not a free service. You have to cover your costs somehow.
Well, that's absolutely right. Yes, we do. So that's a good question. So let's go to our main page. I'm still sharing it. Yes. So here, let's go. I mean, it's a great question. So at the moment we have different plans, right? So what does that mean? We go on a subscription basis, right? A subscription basis. The subscription basis is based on the moon cycle, which is 28 days. So they're 13. In that case, they're actually 13 months per year. So you have these different plans that you can subscribe to. Now, we're not like the rip-off mobile companies, the cell phones, that that your points get reset. Your points get accumulated. If you don't use points, and let's say you use a starter trial, that the monthly cost here would be $19.95, and you get 20 points for it. If you don't use those points, they get accumulated to the next month, and so on. If you decide to cancel your membership, we're very fair. We keep your account for 1 year, and you can come back anytime during the year, and your points will still remain, and so on and so on. Of course, it can get quite expensive, as you can see, but the thing about some of the very big users at iTelescope, when they go to higher plans, they get more discounts. So it's a little bit complicated, right? So they get 90 points, but 90 points can mean something different to one person or the other, depending on what plan they're running. Okay, so does that more or less answer the question? I'm not sure.
Okay, so you had you walked us through an example of Andromeda.
Yeah.
Where you had it set up.
Yep.
And it was a little bit of a moon, but not a full moon. So what would that session typically? How many points would you need to do that?
That's a great question. So it depends again on the, well, let's click on plan 90. Let's just do this for fun. So if you go on this page, I used the link here from the price. You can see, well, that's our education plans. So this automatically gives you the rates. I was using T14. That's 69 per hour, right? So that means 1 hour of imaging would cost 69 points in this case, 69 points. Well, plan 90 gave you 90 points, so you would be able to take Andromeda for 1 hour and still have imaging time. So if you went to plan 40, for example, you wouldn't have sufficient, and also you would see that the rate is actually higher, right? So that's the way it works. So some members actually go to, when we have discounts or so, they go and jump to plan 1000, they collect like 3000 points, and then they go down again and so on. So it's a bit like the stock market, but that's, I know it sounds a little bit complicated, but it's something that seems to work. And you were talking about the moon. Here's the moon discount. So if you got a lot of moon, of course, you can see the rates have gone down drastically, right? So depending on how much moon there is. Okay.
Okay. Do we have any questions for Dr. Sasse? So there's some these are in some pretty unique locations, particularly the southern skies. To be able to capture some of those images there, a ticket to Australia is a lot of money versus being able to do it remotely.
Well, I mean, the southern skies is absolutely phenomenal. I mean, those of you who've been to the southern sky know that you have Sagittarius right up, in winter. We don't have that here, right? It's just incredible. So you have all the beautiful nebula high up, which gives very good seeing conditions. I mean, these observatories are in very good seeing conditions. I mean, it's maybe something in Canada you would only have in, high up in Merritt, I guess. It's probably, I don't know, it's probably one of the best locations that are in Canada for seeing. But it would be difficult to compete, with the conditions. Of course, we have the telescopes are very good. These are typically plane wave telescopes, 17-inch and larger, 20 and so on. And we're also getting a 0.7 meter telescope online very soon. So that's also explained. Well, some of you say, well, the costs seem rather high, but you have to think about the investment costs and also the running costs and so on. It's a lot of work, and it takes a lot of dedication to keep something like this running.
You said you're building a telescope down in Chile as well?
Yeah, that's correct. I mean, we have a partner in Chile, and we're going to probably have an observatory there in a few months. That's correct, because I mean it's just incredible, incredibly good conditions there. Yes.
Super. Okay, well, I don't see any more questions for you right now, but hang on a second.
Okay, sure.
I don't seem to be able to ask a question. Clicking on Q&A just shows me other questions and answers. So, okay, folks, maybe type it in the chat for now. I'll monitor the chat. Our Q&A seems to be broken. Okay.
Dave, this is Chris intervening. There is a question on the Q&A from Michael McGuire saying, can we see any examples of finished photos from one of your scopes?
Oh my goodness, of course, absolutely. Absolutely. Let me share my screen again. Yes. 1 second. Okay, so I'll just go back to iTelescope in a second, and we have different sites. Let's see, here we go. Let's go to the gallery. That's quite nice. We have lots of apods. My goodness, we produce apods, like a conveyor belt. But this is some of the top images that we have, right? God, that's the beautiful Tarantula Nebula that you probably haven't seen like this before. That was an astronomical picture of the day. Oh gosh, Sagittarius triplet and so on. We have quite a few. There's a comet. I don't know which one that was here. Let me see. There was a conjunction of comets here, just beautiful. So we have color. That's another beautiful one here. You can see that was two comets in a star cluster. Damien Peach, who is very well known. He uses our telescopes too. Of course, I mean, yeah, that's an old one of the Tarantula. Let's see what else we have off. I don't know which one. This was a Bubble Nebula and so on. Yeah, that's a famous one. There's a typical star cluster that you have and so on. We have a lot of comet hunters on ours. Very, very common. Lots. That's a beautiful one of the Pleiades. Another comet and so on. Yeah. Oh, that's a very unusual one. That's a very unusual one. You see the Orion and of course the Horsehead Nebula here and the whole region. That looks like that's a big mosaic and so on. These are all the apods. Of course, those are the top images. Member show winners. There's another one here. There are quite a few here. Yeah, it's And a lot of, by the way, you were talking about mergers of black holes, which is really interesting. On the 23rd of August, you actually had it on there too, of 2017. We participated in it without knowing it, and that was the first black hole merger that was seen, and it was also accompanied by a light signal, right? There was a big light signal at that time, and at that time it wasn't. One knew that the gravitational waves were propagating at the speed of light, but there was no real proof. And that was the proof because at that time, when this black hole merger happened on the 23rd of August, 2017, our telescopes were looking right into the west in the constellation of Virgo and seeing Virgo and actually quite a low angle, being able to capture the light that came from this merger. And there were a lot of scientists that were using all our telescopes, and we didn't know about that because it was a completely secretive undertaking. And there were about 3,000 scientists taking part in this incredible undertaking. I mean, of course, as you know, gravitational waves are the most exciting thing we have now, and it's just it's just fantastic. But it is very nice to be able to participate in this. So we do have a lot of science too. A lot of universities participate in programs with us. They have a special education account, so they don't have a subscription and so on. They get about 50% discount, and they use it a lot for student education. They do photometry and many other things on there.
Another question for you. Can you take images of the moon?
We get asked that so often. I would advise you strongly to do it from your backyard. It can be done, but we're not really designed for that. I mean, yes, you can, but honestly, I do it better from my backyard. The same for planets, we get the same. Why is the moon and why are the planets so difficult? Well, the moon is maybe not that difficult, but planets are in general difficult because, as you know, you need quite a long extension for that. You have to have a very long focal length. And it's very difficult to point a remote telescope very accurately to center a planet. We're getting there now because the telescopes are getting better, the software is getting better, but so far, we have we've not accommodated that. Okay, so yes, you can take the moon, but you would have to take it with a narrowband filter H alpha because you need an extremely short exposure, extremely short to do that.
Okay. Any other questions, folks? Either type it in the Q&A or the chat. Okay, I think that is it for the questions. Thank you very much, Dr. Sasse. We really appreciate your time.
It's been a pleasure. Thank you.
You're welcome to hang around and see what else is happening. We've got some amazing images.
Yeah, I'll hang around a bit and then I have to run to my wife because I can't leave her wherever.
Okay, sounds coming up to dinner time there.
Yes, that's right. Thank you. Okay, I'll mute myself.
Thank you. Okay, so Chris is going to bring up his slides here. Okay, so we're going to take a 5-minute bio break, and this is our Messier and Moon challenge. So on the next screen, there's your Messier object, there's your Moon object. See if you can figure out what they are. The answer will be in 5 minutes. Okay, we'll see you shortly. Sorry. Yeah, we probably have 40, 50 images. Okay, folks, we've got about 2 minutes left. Okay, Chris, if you could move on to the next slide. Okay, so we have the Trifid Nebula and Endymion as our two images. So I'm sure some of you recognized those. I know certainly I've seen some of these, certainly the Trifid Nebula, I've seen a number of people capture those images. So we're now going to move into our observation session. We have quite a few images. And first one up is Hugo. So Hugo, are you ready? I don't see Hugo's video there, so I'm not sure whether he's come back. Okay, Chris, why don't we, this is Hugo Lama's images on how to observe meteors. So I thought that was a cute image. You sent that out to our group, and thank you, Hugo, for your image for your cat there. Okay, next one is Jim Thompson.
All right, thanks, Dave. You can hear me all right?
Yes,
okay. Good. So I don't know about everybody else, but I've had a busy summer. Since my last observing report back at the June meeting, I was able to observe on 14 different occasions, mostly from my backyard here in Ottawa, but also a few times from the cottage up on the Ottawa River and once from Foymount, Ontario, a very dark site. The first two images I have to share tonight are mosaics of objects from the evening of June 18th. And I dedicated that evening to observing planetary nebulae. Planetary nebulae are the remnants of sun-sized stars that have reached the end of their life. I observed 21 planetary nebulas in total that night, with the 12 I'm showing here tonight being my favorites. M27 and M57, the top left two images, they are quite bright and can be observed with a telescope visually from in the city if you wanted to give it a try. I chose to use my ASI 294 color camera on a 10-inch Ritchie-Chrétien scope to capture these images. These are all stacks of 5 to 10 minutes worth of 20-second exposures. Some of the planetary nebulae I observed, like Able 39 and 71 in the lower left, were very faint due to their age relative to the other planetary nebulae. Planetary nebulae last only a few tens of thousands of years. The cat's eye was an interesting target in the lower right, but challenging to image because of its very wide dynamic range. In this image, I have saturated the bright center that most people are familiar with, the cat's eye shape, in order to see the faint outer halo. Next image, please. Planetary nebulae are fascinating observing targets due to their wide range of shapes, sizes, and colors, as you can see here. And summertime is a great time to observe these objects because they are commonly found along the Milky Way. Don't ask me where these names come from, though. I have no idea who came up with them, but I just wrote down what Stellarium said they were called. Especially like the cheeseburger nebula. That's kind of a funny name. Next, please. Moving on now to the opposite end of the star's life cycle. On June 19th, I focused my observing on star-forming regions in the Milky Way. Although I did observe all the summer favorites like the Lagoon, the Trifid, the Eagle, and the Swan, I also did a lot of other lesser traveled nebulae like the ones shown here. You will note how these objects can vary widely in size and brightness. I really like the Cocoon Nebula in the upper left because you can clearly see the dark, cold cloud of dust and gas within which the nebula sits. It's almost like a ball of cotton candy on a spoon. Interestingly, the Elephant's Trunk and the surrounding emission nebula IC 1396 that's shown in the lower right, they are at roughly the same distance from the Earth, it and the Cocoon. The elephant's trunk and surrounding nebula appear much larger and dimmer only because that nebula is more mature, and the new stars that were born there have almost finished dissipating the remaining dust and gas. Next slide, please. To take the size comparisons to the extreme, consider these two star-forming regions in Cygnus. IC 1318, also known as the Gamma Cygni Nebula, has a very large angular size at around 3 degrees or 180 arc minutes. In contrast, the nearby Sharpless 2-106 is only 3 arc minutes. This nebula has not only a small angular size from our perspective, but its actual size is also small at only 2 light years. IC 1318, for comparison, is almost 200 light years across. Now, Sharpless 2-106 is small because it is very young. IR imagery of this object has revealed a single massive star forming in this nebula. It is this young star's polar jets that give the nebula its shape. Next slide, please. Much of my July was spent back and forth to our cottage, but I have chosen not to share any of those images tonight. I did manage a few nights viewing Comet Neowise through binoculars while I was there, and that was pretty cool. These images here were captured from my backyard on August 11th, 12th. All were captured with an ASI 385 camera with Baader moon and sky glow filter on my 10-inch Ritchie Chrétien and a 2.5 times Barlow. I captured 3,000 to 4,000 frames, stacking the best 10% in AutoStacker 3 and sharpening them using wavelets in Registax 6. Jupiter and Saturn were captured around 11 p.m. on the 11th, and Mars and Venus were captured around 4:30 a.m. on the 12th. I was pretty happy with how they turned out, considering the seeing is usually not very good for the Ottawa area. Next slide, please. Also on the morning of the 12th, I did some imaging of the last quarter moon. These next 3 images were captured using an ASI 183 monochrome camera with an IR pass filter on my 10-inch Ritchie Chrétien at its native f8. They are stacks of the best 10% of 2,000 frames. This first image is of the region around Sinus Iridum, also known as the Bay of Rainbows. I'm just going to get my annotate tool out here. If you see over here, that is the rim of the crater Plato. The sun is just setting on that crater on this evening. I also like the appearance of these 2 promontories, Laplace and Heraclides. They really stood out nicely on this particular evening. And finally, in this image, I really like this this Rima up here. It's Rima Sharp. It's a valley that I've never observed before, so that was pretty neat. Next image, please. So this next image is of the area around the 93-kilometer diameter crater Copernicus. Copernicus is a brilliant example of a complex crater, having a very prominent central uplift. Actually has 2 peaks in the middle, very clearly defined. It has terraced walls, an impact melt apron, and lots of evidence of secondary impacts from debris ejected from the impact, especially if you look around here. All of those craters are from boulders thrown out from the impact. Copernicus also has a clearly hexagonal shape, as do neighboring craters Kepler over here and Encke down here. And if Simon was here, he would tell us why that is, that they are hexagonal in shape. Other interesting things to note in this image are the volcanic domes that are to the west over here and to the south of Copernicus. I wonder if these volcanoes erupted before or after the Copernicus impact. Also note how bright Kepler is compared to the other craters around it. This suggests that Kepler is significantly younger than its neighbors. The final feature I'd like to point out is the strange bright pattern in the upper left. This is called Rainer gamma. Scientists don't quite know what this feature is. They only know that there is a strong magnetic anomaly in that area that has somehow affected the brightness of the surface material. Next image, please. My last lunar image is of the southern part of the last quarter's terminator. I've rotated the view so south is to the right. This part of the moon, called the Southern Highlands, is considered to be much older than the lava-flooded regions to the north. It is riddled with craters upon craters upon craters. One of my favorite craters is Clavius, which was enjoying a fine sunset on this particular evening. Note the fact that the middle of the crater floor is still illuminated while the perimeter is in shadow. This is because the 231 kilometer diameter crater is large enough for the curvature of the moon to be seen. Kind of neat. Next image, please. On the same evening I was imaging planets and the moon, I was also having a look at the Perseid meteor shower peak. While I was using my 10-inch scope, I also had a camera on an 8mm fisheye lens taking images every 60 seconds. I captured 12 meteors in total through the course of the evening, 7 of which were Perseids. This image is of a bright fireball I captured at 2:52 a.m. I figure it was around -1 magnitude. For reference in this image, Cassiopeia is right here. Perseus is here. The faint glow right here is the Heart and Soul Nebula. North American Nebula is up there. And this is Mars right here. And the bright thing entering the scene at the bottom was the moon. It was just starting to come up at that point. And finally, my last image is from the evening of August 19th. In it, I have returned to IC13 in Cygnus. This time I have used a 135mm camera lens on my Skyraider DS432 monochrome camera in order to show the full extent of this large star-forming region. The field of view in this image is roughly 5 degrees across. Also captured in this image is NGC 6888, the Crescent Nebula, down here. This object is formed by the extremely powerful solar winds from the massive Wolf-Rayet type star in the middle, so right here. These high-speed flows are crashing into the surrounding gas that was thrown off by the star earlier in its life while it was a red giant. The gases are then made to glow by the prodigious UV radiation coming off of the hot star. The star is thought to be 600,000 times brighter than our sun and 21 times more massive. It is at the end of its life and is expected to explode as a supernova in the next couple 100,000 of years. And that's it. Thank you.
Thanks, Jim. So we're going to move on to Calvin.
Thanks for that. I lost at least half an hour where my internet failed, and I eventually reset the router, and I'm back. So this is an interesting photo. This is sort of more for fun. You'll recognize the North American Nebula there, and the Pelican Nebula. This is imaged in August 15th from my cottage in La Pêche, just north of Ottawa, the Bortle 3 skies. I used the RASC 8 ROAC instrument astrograph, and I use a one-shot color CMOS camera from ZWO. So I use the dual band filter right now. Like we're in nebula season, I guess, for me. Like I'm struggling to find good galaxies to image. So I'm playing around with different nebulae. So this one I posted on Facebook, the original photo with all the stars included. And I had a friend complain that the stars were kind of cluttering up the beautiful nebula behind it. So I thought, oh, that's a good opportunity for me to play with the StarNet software that will remove stars. So actually the camera's very big images coming out of this camera. So it took forever. And I did each color, the RGB channels separately, and then I welded them back together again. And that's the image. So I just think it's very spectacular and fun image. And I use it as my background. You'll see it behind me here as well.
Okay, thank you, Calvin. So we're going to move on to Brian Carroll.
Howdy. The lunar challenge was Eratosthenes. So this is my image of Eratosthenes. You can see the central peak, and you can also wind up seeing the double shelf of the crater rim. Now, people who are new to lunar astronomy can be intimidated by trying to find their way around the moon's complex surface. So I thought I'd show beginners how to find Eratosthenes. Next slide, please, Chris. So with binoculars, you can wind up, or a small telescope, you can have a view like this. And what you look for is 3 Maria, Mare Imbrium, Mare Serenitatis, and Mare Vaporum. And you'll see a string of mountains between those. You can actually see Eratosthenes with binoculars, but I'm going to zoom in with a view of what it would look like through a small telescope. Next slide, please, Chris. So again, Mare Imbrium, Mare Serenitatis, Mare Vaporum. The mountains that you're seeing are Montes Apenninus. And if we zoom once more, please, Chris, then you follow the arc of the Montes Apenninus and you find Eratosthenes. And those are my images for this evening. Thanks, Chris.
Thank you very much. Next one is Richard. There we go.
Good evening. I had a wonderful August. I rented a cottage for the family just 2 kilometers away from the Dark Sky Preserve in North Frontenac. So even though I didn't actually go out to the observing platform, I had a beautiful view from the lawn of the cottage out over a lake, and perfect views of the southern skies. It was wonderful. Except, of course, the weather was not as great this year. We had a lot of cloudy nights. Anyway, so these are some of the personal challenges that I had with my new telescope. It's the William Optics Z73 Zenith Star and the Canon M100 mirrorless camera attached to it. So this first one is the Helix Nebula in Aquarius, a very, very faint planetary nebula, but it came out quite nicely with 30-second exposures at, I believe this is its ISO 1600. Next one, please. Another planetary, of course, the Dumbbell Nebula, higher in the sky. Getting a little bit of the green and red on it. It was quite a nice view of that. Next one, please. And of course, we couldn't miss taking pictures of the Trifid and the Lagoon nebulas in the south in Sagittarius. This again is one of the best views I've had of these two nebula. Next one. Now, there's a little backstory about the Andromeda Galaxy, a personal challenge for me. Now, if you're looking at my personal video, my face up here, I'm just going to turn off the virtual background here so you can see where I'm doing it from. And on the wall of my study here is a very old photograph, probably taken in the 1970s or even the 60s by a professional astronomer, a colleague of my father-in-law, Jacques Lebrec. And I've had that, well, it was on my father-in-law's wall, it's now on my wall for many, many years. And it's been my challenge to try and get a photograph as good as that of the Andromeda Nebula. So this year, I think I made it. So again, this is 30-second exposure. I believe this one was actually ISO 6400, about 30 or 40 images at 30 seconds each. And I've got just about the same level of detail in all the dust lanes. The stars are not quite as small, so I still have some work to do in getting sharper images. Next one, please. Again, in the southern skies, the Eagle Nebula M16, and in the center, the heart of the Eagle, of course, is the Pillars of Creation that was made famous in the Hubble photograph. Next one. After looking at the Andromeda Galaxy, of course, just move a little bit farther to the east, and in Triangulum, you'll find this lovely Whirlpool Nebula, Whirlpool Galaxy, almost as bright as the Andromeda Galaxy, but not quite as large. Next one, please. This is my background for tonight. And if you remember a couple of months ago when we had the session on tips and tricks about things you can make for your telescopes, I showed a little crosshair device to put across the front objective of the telescope. So I'd been waiting to get a picture of the Pleiades, and about 2 in the morning, they were finally high enough in the sky. I slipped on the tin can with my fishing line across it and got this lovely sparkly picture of the Pleiades, and yet with a bit of the nebulosity as well. So I'm very pleased with that. And of course, if anybody has a Subaru, you'll recognize the logo of the Subaru cars. Next one, please. Towards the end of our cottage stay, the moon started getting a little bit larger and brighter. So I aimed the telescope at the moon and tried a few different experiments with different combinations of direct camera attachment and eyepiece projection. This was with the eyepiece projection. So I got a fairly nice big view of the moon. And then when I got home and processed it, it just happened that the Sky News arrived that day, and it pointed out that on the first quarter moon like this is, you can see 2 particular features, the lunar X and the lunar V. Just a particular shadow pattern that happens along the terminator just at the time of around the first quarter moon. So I had coincidentally captured those quite nicely on this image. Next one, please. This is one of the beginner challenges for the month of August, M55, a globular cluster down in Scorpius. Next one, please. And then there was a bit more of a challenging object for me. I was aiming at M52, but happened to notice that the Bubble Nebula was very close by. And when I processed the picture, I found that there's yet another NGC object, NGC 7538, on the far left of the image. So 3 for the price of 1. The bubble nebula is a very, very faint structure. You can only see maybe a third of the circle there, but of course, if you take a longer exposure, you can sometimes get a complete circle making the bubble. Next one, please. This is again with my crosshairs, fishing line crosshairs. This is sometimes called the owl cluster in Cassiopeia, also known as the ET cluster. It was also featured on the Royal Astronomical Society calendar this year, I think for the month of June or July. A very similar image to this. Next one, please. And finally, here's my view of the North America and Pelican nebulas. This one with all the stars. I didn't know you could take all the stars out. I'll have to see if I can find that software. Anyway, this is the more realistic view of it with all the stars in place. This one again is ISO 6400, 30-second exposures, about 40 images stacked up. And I still have a few left on my files to process. So next month I'll show a few more of those. I also got a few pictures of the asteroid Ceres as it came around to its opposition. So I'll see if I can get those processed for next time. Thank you.
Okay, thank you, Richard. Great collection of images there. We're going to turn it over to Jim.
Okay, thank you. Can you hear me well?
Yeah, you just say you're a little bit better now. Just speak loudly.
Okay, very good. Okay, so this is NGC 7380, the Wizard Nebula. This is an emission nebula in the constellation Cepheus, taken with the Mellencamp Skyraider 10C and my 8-inch Smith Cassegrain. This is an interplay of stars, gas, and dust spanning 100 light years at a distance of about 7,200 light years away. I presented the Wizard to you in July, but I prefer this image, which I took a couple of weeks ago. This is a live stack of 15 20-second exposures, totaling 5 consecutive minutes of stacking. Now, with my current Alt-Az evolution mount, star trails would have been evident in this image. But fortunately, if the image is, if there's enough contrast and stars, I can use a feature of Mellencamp Sky software called Deep Sky Stacking, which aligns the stars during the stacking process, as you can see. During that time, I can also take advantage of software features such as manipulating the histogram and other settings to enhance the image on the fly. This, the filter that was used here was the Optolong L-Enhance narrowband filter. And this image and the ones that follow were post-processed using Topaz Studio. Next one, please. This is M57. I never get tired of this beautiful planetary. I enjoy the range of color emitted from the Ring Nebula, and I'm always curious about the transparency I will get in the central core area. This is a stack of 15 20-second exposures with the same equipment. Next one, please. And this is M76, the Little Dumbbell, a planetary nebula in Perseus, which lies about 2,500 light years from Earth. The Little Dumbbell Nebula is sometimes called the Cork Nebula or the Barbell Nebula. And this is a stack of 15 20-second exposures. Next one, please. And this is the Bubble Nebula, NGC 7635, another favorite of mine. This is an H2 region emission nebula in the constellation Cassiopeia. The bubble is created by the stellar wind from a massive, hot, 8.7 magnitude young central star. According to NASA reports, this star burns 1 million times brighter than our sun and produces powerful gaseous outflows called stellar winds that howl at more than 4 million miles per hour. Based on the rate the star is expending energy, scientists estimate that between 10 and 20 million years from now, it will explode as a supernova. And the bubble will, and I quote, pop. This is a stack of 15, 18-second exposures. Next one, please. So these are two, this is planet Saturn, which I took with a beta UV IR cut filter and a PowerMate 2X. Next one, please. And this is Mars. Maybe I should increase the power on that PowerMate. Nevertheless, I really enjoyed this image because I got some detail, and that's what I was looking for. And I'm hoping to catch Mars at a later elevation later on this month and next month as well. So let's take advantage of this opportunity. Well, I'm done. Thank you very much.
Okay, thank you. So we're over to Doug George.
Hello. So some of the people who have been around for a while know that I founded Diffraction Limited some years ago, and we make a few products like Maximum DL and Bolt Cloud sensors. And about 6 years ago, we acquired SBIG, which is formerly a California company. And since then, I've been spending much of my time designing cameras. And I not only have the fun of designing the cameras, I have the fun of being the first person to try them out. So this is an image from our new STC7. It's called the STC7 for a few reasons. One, it harkens back to one of SBIG's original cameras, the ST7. Another reason is it's CMOS, so it's STC. Never mind that CCD also starts with a C. And the other reason is that it comes complete with 7 built-in filters with luminance, red, green, blue, hydrogen alpha, sulfur 2, and oxygen 3. So I put this in my backyard telescope and down in Barrhaven, and it's on an FSQ 106 refractor. And this is a couple hours exposure in hydrogen alpha with the new camera. And I'm quite pleased with the results. It shows a great amount of detail in the Crescent Nebula itself, but also an amazing amount of stuff behind the nebula. Lots of fine structure there. I found sometimes the, I'm gonna go to the next picture. Sometimes the black and white pictures just look so much more interesting, so much more detail than the color do. This, of course, is a North American, which has been featured a few times this meeting already. But I particularly like the beautiful contrast here and the resolution of the camera. So this is working out extremely well, and I'm really pleased. And this is just luminance; it's not a narrowband image, so it's actually working out to be quite sensitive. If we go on to the next frame, this is the Western Veil Nebula. Now in this case, the moon was up, so I made use of the narrowband filters and assigned each of the 3 filters, the hydrogen alpha, the sulfur 2, and the oxygen 3 to red, green, and blue to make this false color composite. And it really shows up the fine structures in the nebula, and also that a huge amount of detail off to the left side of the main part of the nebula. This whole region is just full of all sorts of really interesting nebulosity. I especially like the fine tendrils on the left side of the image. And the fourth and final image is the other half of the Veil Nebula. Again, shot with narrowband filters, and you can see it looks remarkably different in terms of the colors and such that appear. So what we're seeing with the different colors is different ionization levels of the gas. So different atoms are ionized to different levels and producing these various colors. And so you can see the nebula is differentiated by materials and by ionization level, which tells you something about the physics that are going on inside the nebula. The Veil Nebula is, of course, an enormous supernova remnant from many thousands of years ago, which has been expanding across a very, very large area of the constellation Cygnus. And that's it for now. I have another new camera, which I hope to test out in the next couple weeks, and hopefully I'll be able to come back and show you some more images.
Doug, while you're there, it's Chris taking advantage of my ability to turn my microphone on. I had to chuckle in Christian Sasse's talk. By the way, he's no longer on this on the Zoom meeting, where he gave credit to Maxim and Boltwood Cloud Sensors is developed by some Canadian. Did he know that some Canadian was here in the meeting tonight and presenting?
Yes, and listening to him say that was quite amusing.
It was nice to see your products in use there.
Thank you.
Maybe at some point, Doug, you can give us some overviews of your camera as a presentation.
Absolutely, I'd love to do that. Maybe when I'm a little bit less busy, so I can do proper presentation on it. Maybe in a few months.
Yeah. Okay, well, thank you for your images, and we're going to turn it over to our resident lunatic, Brian. Welcome aboard.
There, am I unmuted?
Yeah, you're good.
Okay, unmuted now? Okay, good evening, everybody. Salut à Montréal. Here are my stunning lunar images. I know they really stack up against what we've seen already, but the image on the left, I was doing the moon and trying to capture Mars at the same time. On that particular image, I was using a new Windows program, which means I was shooting through the upstairs bedroom window to get it. The shot on the right was the very next morning. I was out having my coffee, putting the cat out, and hoping the cat would run away, but it didn't. And managed to, I looked to see where Mars would be, and I found it with binoculars, and then I could see it. Then I could see it naked eye. So I've got the comparison image. Next one, please, Chris. So the lunar challenge, crater Eratosthenes. This was from one of my images from some time, one of my fuzzy lunar images. So there it is there. Just while we're right in this area, if we go to the next slide, please, Chris, thank you. So when you're looking around in that area, you're right around the Apollo 15 landing site. Now, we'll go to the next image. We're going to take a little diversion just to look at that landing site. And Stephen McIntyre, we could go to the next one, please, Chris. Stephen McIntyre very kindly let me use this image that he took. This is one from 2018. And you can see over on the right where he's got the Apollo 15 landing site marked, and you see the small rill, that little valley right there running along there. That's Hadley Rill, and you see here's Mount Hadley here and Mount Hadley Delta down here. So when those guys came in with their spacecraft, they had to drop it down over the mountains and plug her down in a fairly tight space. Now, just while we're looking at this image, this is Stephen, this is a super image. I know you're watching tonight. This is great. The large crater that you see on the left is Archimedes. And it's about 140 kilometers in diameter, but you see it's a very flooded crater, very smooth inside. But over to the right, running across to where the Apollo 15 site is, that's what they call the Palus Putridinus, the Marsh of Decay. And that's about if you were to jump in your car and drive from Archimedes over to the Apollo 15 landing site at about 110 kilometers an hour, it'll take you about 3 hours. It'd be about a 3-hour drive. All right. And you see down below Archimedes there, you see all the uplift there, and it's sometimes known as the lower Apennine Highlands or Montes Archimedes. So where Apollo 15, all that area is on the right, that's all the Apennine Mountains. Okay, if we could go to the next one, please. All right, so I've named a few things. So I put the main craters in blue. So we see Archimedes up at the top there again, and Palus Putridinus, the Marsh of Decay. And so you can see where Apollo 15 then is tucked in just in the corner there. But you see the arc of the Apennine Mountains, and you can see already that it's describing an arc of a circle, which is what most arcs do, but it's the outer rim of Mare Imbrium. So the big Sea of Rains was one of the last major impacts on the moon, and when it developed 3.85 billion years ago, and of course everything gets blasted to the sides, and you end up with all the uplifted mountains. And here you've got the crater Eratosthenes hanging off the end of the Apennine mountain range. It's a beautiful area to look at. And what I liked about when I saw Stephen McIntyre's images there a couple months ago, I was just blown away by this because he presented it, and I'll show you the larger view of this in just a moment, but it's just the orientation that he had it on. And what I find about this area, it's one of the most interesting areas to me on the moon, because it looks like there are different places that you could drive around and visit. You could go and park your car. You could climb up the side of the crater there. I mean, you see Eratosthenes down there. That's about 58 kilometers in diameter. Copernicus down at the bottom, 93. And you've got all the other mare there that Brian Carroll mentioned already, Mare Vaporum, right? And if you climb right to the top up here, this is where you're getting to the, it's called Promontorium Fresnel, the Fresnel Promontory. So this is just a little gateway. On the left is Mare Imbrium, on the right is the Sea of Serenity. All right, so let's, I'll just show you one more thing on this image while we've got it here. It shows up so well, Stephen, thank you. Is the flooded crater Stadius. So it's just like a ghost crater right here, as is crater Wallace. So if you're looking with even low power telescope, start seeing what you can make of some of these features. And if we go to the next image, please, Chris, thank you. So here it is, and I just love this. It's kind of an unusual cropping on a vertical view like this, and I just love it. So toward the top, I mean, you can see Plato, that's been mentioned already. Here's the Alpine Valley, right? So this is the Alps region. But here's where we were looking at before. Here's the Apollo 15 site down here. Here's the Fresnel Promontory. So it's just a little narrow gateway to the Caucasus Mountains here, and a little flooded gateway into the Sea of Serenity. So it's almost like if you're going from the open ocean into the Mediterranean Sea, you got that tiny narrow gateway, and there's lots to look at. There's lots to look at around there. But now you can start to see the arc that's been formed here. And when we saw Jim's earlier image that was showing a bit farther to the west, so he was looking up around Mare Frigoris, the frozen sea along here, and to Sinus Roris was that bay, and this is where he was looking at some features there. And you start to get a real sense of how a strong impact can affect a body in space like that. And it blasted everything. The crater eventually bubbled up with the molten material and settled down. You see wrinkle ridges, right? All these things here. So as the molten material was cooling and condensing, everything got scrunched up. But there's in an image like this, you could spend the rest of your life exploring this and having a ball. Thanks, Stephen, for lending me your images. Thank you.
Okay, so we're actually talking about Stephen. He is up next.
Yeah, there I'm on. Yeah, thanks, Brian, for all the accolades. Last Saturday, we had a very nice conjunction of the Moon and Mars. I snapped this image at about 12:28. It was about 2 minutes before closest approach, which would have been 43 arc minutes. I was hoping to catch a picture of exactly that closest approach. This is a single frame using my 80mm f4.8 refractor, Canon 80D at 1/500th of a second at ISO 200. The conjunction was actually visible anytime like after 10 when the moon rose. So Mars was sort of hovering around the moon for that whole time, except for the fact that it was mostly cloudy in Ottawa. Despite that, I still set up my scope on the front porch in the early evening, kind of hoping that it would break. The CSC actually said it was clear that evening, but looking outside, it wasn't. I tossed a tarp over it, just kind of pressing it, which is a good idea because at 10:30 I looked out and it was pouring rain. So I brought the scope in, thinking the night was done. But at about 12:15, I went back out and there was a good sized break in the clouds. So I lugged the scope back out again and started taking some test images. And I was in the process of taking test images, like 11:28 was the last image I got. 11:29, the moon had disappeared from the camera, and I looked up and the clouds had rolled in again. So, all right, no closest approach image, but fortunately the 11:28 image was actually in focus and a decent exposure, so that worked. I'd also wanted to take a wide angle shot because I don't know, the moon with a red dot next to it isn't like the most interesting composition for a conjunction. So I wanted a wide angle shot with the foreground, but again, the clouds had rolled in, so no such luck with that. but anyway, actually, I find like a conjunction type of event is much better in person anyways. You can take a photograph of it, but actually looking up at the sky and kind of seeing this close approach is a lot better in person than a photograph can do. All right, back to you, Dave.
Okay, thank you very much, Stephen. Bob, you're up.
Yeah, how do you do? This is one of the challenge. This is one of the challenge objects that was given to us. It's for me, it's very low in the sky. I've got trees in that direction, so it's tough to get much time on it. But this is M55, Messier's list of things that were not comets. It's one of the things about it that I sort of thought was interesting was that it's 12.3 billion years old. So it's one of the first things that formed in the universe. Very, very wild. And it's about 250,000 stars, about. Okay, next image, please. This is another challenge object. It's the blinking nebula. It's called that because in small telescopes, the central star will fool your eye and you'll not see the nebula part. So the nebula part blinks in and out. This was taken with a long focal length telescope and was cropped after that. So this thing is pretty small. Okay, next image. This is called the Ghost in Cepheus for obvious reasons. I'm actually going to revisit this a little later on this summer if I have time to, because there's some supernova remnants in this image, which I can just barely see. And I think they need a little bit of hydrogen alpha they're red. To see better. Still, kind of a weird character, isn't it? Next image. We've seen this image several times tonight. It's high in the sky, and so it's fun to see. And it's called the Wizard. It's difficult to see visually because we don't see red very well. We can see the star cluster that's in it, but not the Wizard. I have no idea why it's called the Wizard. Maybe somebody can chip in sometime and let me know. Okay, next image. And this is the ever-present bubble nebula, which I actually know why it's called the bubble nebula. Its central star has been pointed out already tonight, is blasting this bubble out of the sky. And it's about 44 stellar masses. That's a big, bright star. Will not last long. Anyway, thank you very much.
Okay, thank you, Bob. And Paul Cleninger.
Thank you, Dave. Can you hear me okay?
Yep.
All right. Well, hi, everybody. I've got a few observations to share with you tonight of places both near and far. So I'll start with the close ones. Well, after putting on an amazing show for us in July, our friend Comet Neowise was still hanging around last month. I took this image 4 days after our last meeting when a fortunate opportunity also presented itself. Next slide, please, Chris. On the night of August the 11th, another comet Pan-STARRS, passed less than 3 degrees from Comet Neowise. You may remember Comet Pan-STARRS from earlier this year. Next one, please. Back in late May, I observed this comet as it passed very close to galaxies M81 and M82 up near the Big Dipper. At that time, it was about 1.7 astronomical units from Earth, and it had just passed its closest approach to the Sun 3 weeks earlier. Next one, please. Fast forward 11 weeks, and it had moved from Ursa Major down to Boötes, the region where Comet Neowise was also sailing through. Pan-STARRS was then about 2.4 astronomical units away from Earth, whereas Neowise was just around 1 astronomical unit away. Fortunately, Pan-STARRS had remained bright enough and big enough to show itself fairly easily against Neowise in this image. Comet Neowise itself was no longer visible to the naked eye at this time, but still a relatively easy catch in binoculars. I could see at least 2 degrees of its fan-shaped dust tail through my 15 by 70 binos. Next one, please. And just a bit of a closer look here at Comet Pan-STARRS. Well, that night was a bonus. 2 comets for the price of 1, a bit of a celestial bargain. All right, next one, please. So on the following night, August the 12th, the sky was pretty clear out my way. And so I did a bit of a Perseid watch and tried to bag a few meteors up against the Milky Way as a backdrop. This was taken with a 16mm lens and Canon 60DA. Unfortunately, the moon was up shortly after midnight that evening, which wiped out a lot of the fainter Perseids. But I did manage to capture a few and saw about 24 pretty decent meteors before packing it in for the evening. Next one, please. So a little further afield, Mars has been becoming increasingly bright and rising earlier in the evening sky as it heads for its closest approach to Earth in just 3.5 weeks from now, on October the 6th. At that time, it'll outshine even Jupiter in the night sky, and it won't be as close to us again until the year 2035. I took this image of Mars last Sunday morning when it was only about 2/3 of a degree above the moon. It was quite prominent in its ruddy brightness, even against the moon's glare. I used a 500mm Optica lens with a Canon 70D for this view. You should try to catch Mars through a telescope if you can over the next few weeks, as it'll appear large enough to show surface features such as its southern polar cap and darker regions such as Syrtis Major. Hopefully there won't be any major dust storms whipping up in the next little while to steal the view from us. Next one, please. So the last two observations I have tonight, I'm venturing out into the depths again. These are a couple of peculiar objects that are much farther away. They're quasars. For those who aren't familiar with these beasties, I'd like to offer a bit of context, just to put them in a bit of background on them, just to put them in context before I show you the images. Quasars are amongst the most luminous and some of the most distant objects observable by both professional and amateur astronomers like us alike. They're enormously energetic nuclei at the heart of very active galaxies. In fact, they're insanely energetic, with the most powerful ones being thousands of times more luminous than an entire galaxy like our Milky Way. Quasars were only discovered in the late 1950s with the advent of radio astronomy and remained enigmatic objects for quite some time because some of their properties seem truly bizarre and even contradictory. While they were observed to emit copious amounts of energy in radio and even X-ray frequencies, there were no obvious source objects visible at optical frequencies. At best, only a few star-like point sources seemed associated with some of the radio sources. In fact, it's from these star-like point sources that the term quasar originates. It's a bit of a contraction of sorts from their original description as quasi-stellar radio sources. As more research was conducted on these objects, it just seemed that they got more and more strange. Luminosity variations occurred very rapidly for some of them, suggesting that whatever they were small, perhaps less than a light year across, and for still others, possibly only about the size of our solar system. And yet other research into their spectra indicated redshift amounts that, if true, would translate into cosmological distances, putting them at billions of light years from the Earth. No process understood at the time could explain how an object could be that small and yet powerful enough to generate energies detectable across an appreciable fraction of the observable universe's size. It took a number of decades of advancement in our knowledge and acceptance of black holes as real, along with deciphering the expansion of the universe and also piecing together the cosmological evolution of galaxies from the earliest times, to finally understand what these objects might really be. Today, we believe that the majority of galaxies likely harbor supermassive black holes at their centers. Their masses range from millions of times to the mass of the sun, such as the one at the center of our own Milky Way, to billions of solar masses, like the one first photographed last April in the heart of galaxy M87. And it's a supermassive black hole that can generate the crazy energies powering the quasar's emissions. More precisely, it's the gravitational stresses and the enormous friction of the matter being drawn in towards the black hole and forming an accretion disk around it that generates the energies. And this energy can be released across the entire electromagnetic spectrum, from gamma rays to optical frequencies and into the radio wavelengths. It's been calculated that in this truly extreme environment, between 6 to 32% of the infalling matter can be totally converted to energy. That's crazy. In comparison, the fusion process that powers our sun converts just 0.7 of 1% of the chain reaction ingredient's mass to energy. While quasars have been discovered as close as 600 million light years from us, the majority of them are much farther away, implying that quasars were more common in the early history of the universe. That makes sense, since galaxies in the early stages of their evolution would have included much more loose raw materials than galaxies at the present time, thereby providing a rich feeding ground for their central supermassive black holes. It's been calculated that a typical quasar today converts the equivalent of 10 suns worth of mass to pure energy every year, while the most energetic quasars devour 1,000 solar masses every year. And about 10% of the quasars are seen to have enormous energetic jets blasting away from them, as shown in this artist's conception. Next slide, please. So the first quasar ever to be identified is known as 3C 273.0. It's in the constellation Virgo, and it also is the brightest known quasar. It's actually so bright that at magnitude 12.8, it can be observed visually in a relatively small telescope. Next one, please. Just as a star of that magnitude would, but instead of just a few dozen or a few hundred light years away, it's actually 2.5 billion light years distant. Next one, please. But a deep exposure reveals more. 3C 273 is among the group of quasars that has a jet emanating from its billion solar mass central black hole. It's the jet that I was hoping to capture. It's very much fainter than the galaxy itself, and only than the quasar itself, and only about 1 arc second in width. This is a combined 2.5-hour LRGB exposure with the 11-inch Edge HD at f10 and a QHY9M CCD camera. It was really challenging to get this. The majority of the almost 10 hours of images I took had to be discarded because either the seeing conditions, the sky transparency, or the tracking were just not good enough to record the jet. But I was eventually lucky enough to have it register and also record the many faint, distant galaxies you see in this image. In fact, most of the things that you see in this image are in fact galaxies, not stars. Next one, please. This slide shows a few views of 3C 273 and its jet, including images from NOAA, the Sloan Digital Sky Survey, and the Hubble Space Telescope. I've sized the NOAA and the Sloan images to be roughly the same scale as mine, and the Hubble image at about 4 times my scale. That image shows the jet to actually have a pretty complex internal structure of knots and twists. It's also known to be emanating its energies at X-ray, radio, and infrared frequencies, in addition to the optical wavelengths. One of the things that really struck me about this jet and made it an interesting target is its size. So I'd like to put that in perspective. Next one, please. So most of us are familiar with our next door neighbor in space, the Andromeda Galaxy. We've seen a few images of that already tonight. That galaxy is 2.5 million light years from us. Quasar 3C 273 is 1,000 times farther away at 2.5 billion light years distant. Next, please. So if the Andromeda Galaxy were right beside that quasar, this is how it would look. This is how it would appear to us. What jumps out of this comparison is the fact that the jet blasting out from the core of the quasar is as long as the Andromeda Galaxy is wide. That's freaky. Quasar 3C 273 truly is an impressive powerhouse, but probably not in a galaxy you'd want to live in with a blowtorch like that flaming nearby. That just can't be very healthy. All right, the next one, please. My final object is also a quasar, but interesting to me for different reasons. It's known as a twin quasar and was one of our challenge objects not too long ago. Like 3C 273, it can also be observed visually, but requires pretty dark skies and a larger size telescope. It's located just off the bowl of the Big Dipper. Next one, please. Even though it's much fainter than 3C 273, This is actually an easier object to locate since it's just a short 10 arc-minute hop away from the edge-on spiral galaxy NGC 3079. Its two components look just like a couple of magnitude 16.6 stars separated by about 6 arc seconds. Next one, please. So my deep exposure of this object is a combined 2-hour image taken with the 11-inch HD and an SBIG ST10 XME CCD camera. What fascinates me about the twin quasar is that it's actually just one object, and it's 8.7 billion light years away. That's over halfway across the observable universe. How can we possibly see such a distant object, even though it's a very luminous quasar? And how can it be just one object? The answer to both these questions is that this quasar is actually a gravitationally lensed object. In fact, the twin quasar is the first gravitationally lensed object ever identified, and it was only discovered in 1979. For those not familiar with the concept, gravitational lensing is the bending of the shape of space-time caused by a massive object, such as a galaxy or even a whole cluster of galaxies. Such warping effectively creates an enormous lens in space, allowing the light of very distant, otherwise unobservable objects to be magnified and brightened. But such lenses aren't perfect in shape and thereby cause distortions in the appearance of the distant background objects. Those distortions can include altering the appearance of the object, much like a funhouse mirror does, or creating duplicate images of an object. That's the situation with the twin quasar. Next one, please. While it's called the twin quasar, a closer look does show a subtle difference between the pair, such as the apparent haze surrounding the component on the upper left. The Hubble Space Telescope has been used for such a closer look, and here's what it saw. Next one, please. The gravitational lensing of this quasar is caused by the cluster of galaxies surrounding the two bright star-like images. One of these galaxies is almost exactly directly in our line of sight with the upper left member, with the indicated core being only 1 arc second removed from it. Actually, the next one there, please, Chris. That's the core of that foreground elliptical galaxy. This is a giant elliptical galaxy, and this seemed to be the source of that haze surrounding the one component of the twin quasar. That galaxy has been determined to be about 3.7 billion light years from Earth, less than half the actual distance to the quasar, whose light it's magnifying and distorting. Next one, please. So in summary, the discovery and understanding of quasars has helped to shape our understanding of the universe as a whole. Their enormous luminosities and incredible distances also give us, even as amateur astronomers, glimpses of objects in distant reaches of the universe. As Spock might say, fascinating. Thank you.
Hey, thank you, Paul. Just give me a second here to reset things. There we go. There, we're back. Okay, so our observing challenge last month was M55 NGC 6826. Was our intermediate challenge. Advanced challenge was IC 4732, and the lunar challenge creator Eratosthenes. Sorry, tongue twister there. And it looks like some of the folks with their observations were able to capture those. Next one. So our beginner challenge is going to be Messier 110. It's a satellite galaxy of the Andromeda Galaxy. It's a dwarf elliptical galaxy, magnitude 8.92. Next one. Intermediate challenge is NGC 7354. It's a planetary nebula in Cephas, 12.9 magnitude. Our advanced challenge is Polymorph 13. It's a globular cluster in Pegasus, 13.47 magnitude, 2.2 arc minute diameter. That's going to be a tough one to image. Okay. And our lunar challenge is Crater Timocharys, and it's in Mare Imbrium, 34 kilometers in diameter and 3.1 kilometers deep. So that'll be your moon challenge for this month. And there's a summary of it. So thank you for Oscar for pulling those together for us. And moving on. Okay, so the Fred Lawson Observatory is open. We have to respect social and physical distancing rules. So far, things seem to have gone well there, and members are welcome to visit that observatory. Encourage you to exchange some emails when you are going, just to make sure we don't have too many people there. Okay. Well, the museum is closed, and that means our library is closed right now. We have been in conversation. We've had some conversations with the museum, and I don't foresee us going there anytime soon at this point. And we'll probably be the new year, but we don't know. There's a lot of things they're working on right now. They're just scrambling to get themselves open. Okay, next. Here are the folks that ensure the club is running smoothly. Next one. So thank you. I didn't see what the count was. Chris, do you have a rough idea?
At maximum, I saw 91 people. That typically translates into over 100 unique people that would have come and gone during the meeting. So again, great numbers during COVID.
Yes, absolutely. Yeah, that's really appreciate that. Okay, no post-meeting entertainment right now. Again, once hopefully into the new year or when things settle down, we'll be able to resume those type of things. So if you'd like to become a member of the Royal Astronomical Society of Canada, regular membership is $88. Family membership is $82.50 plus $15 an adult and $8.10 per youth. That's a really good deal. My wife and I are members, and my son is also a member, so that works out economically quite well. Youth membership is $53 if you're under 21 years old, or under 25 if you are still being a student. If COVID is causing you financial pain on renewal of your membership, please email president@ottawa.rasc.ca. We do have some funds to assist you with that. Membership benefits of being a member of the Royal Astronomical Society of Canada. We have the Ted Bean Loan Library, where you can borrow a telescope from us. Once the museum reopens, we have the Stan Mott Library. I've already mentioned the Fred Lawson Observatory out near Almont, which is our private observatory site. Also, you get the Sky News every 2 months, the Journal every month, the Observer's Handbook sort of towards the end of the year, ready for the following year. And we have our local astronauts, which are put together by Gordon Webster, excellent monthly publication of images and articles by our local members. So our next meeting is going to be October the 2nd. It will be a Zoom webinar. And we have 2 guest speakers at this meeting. We have our own Simon Hamner, who's going to be talking about Mars science. And we have Dr. Renee Doyon talking about the James Webb Sky Telescope. So it's going to be an interesting meeting. Again, we'll have some observations as well. So it is October the 2nd, Friday, October the 2nd. And we'll see you folks there. Any other slides, Chris? Nope, that is it. So thank you very much, folks. That wasn't too bad. We only went about 7 or 8 minutes over time. Appreciate you coming out. And I'm always looking for suggestions for upcoming meetings in terms of guest speakers and so on and so forth. We are going to have a special joint meeting with Montreal on December the 6th. That's a Sunday, Sunday at 5 o'clock. And I will be sending out a notice to you folks about that. And we have a Canadian scientist who's involved with the planetary rover. She's one of the drivers, and it's going to be an excellent presentation. So I'll be sending you details out about that. It'll be a webinar hosted jointly between Ottawa and Montreal. So thank you for coming out, and we'll see you folks next weekend. Stay safe.